Welcome to Lesson 4, the second part of our weight and balance course. In Lesson 4, we will cover some additional terms used in aviation weight and balance, as well as going over some examples of how to calculate the empty weight and empty weight center of gravity for aircraft after they have been weighed. It is important to note that not everything we will need to know and understand will be covered in these lessons. Additional and more in-depth information will be found in FAA publication 8083-30, the Aviation Maintenance Technician's Handbook, General, Chapter 4, as well as the FAA's Aircraft Weight and Balance Handbook, which can be downloaded from FAA.gov or viewed in the course content section of this course. The maximum weight of an aircraft is the maximum legal weight at which an aircraft may be operated. The same aircraft flown in different categories may have different maximum weights. The empty weight of an aircraft includes all operating equipment that has a fixed location and is actually installed in the aircraft. It also includes the weight of the airframe, power plant, required equipment, optional or special equipment, fixed or permanent ballast, hydraulic fluid, and residual fuel and oil as indicated in the aircraft specifications or type certificate data sheet. As stated earlier, excessive weight negatively affects the efficiency and operational safety of the aircraft. The load factor is the ratio of the maximum load an aircraft can sustain to the total weight of the aircraft. An aircraft operated in the normal category must have a load factor of at least 3.8. An aircraft operated in the utility category must have a load factor of at least 4.4, and an aircraft operated in the acrobatic category must have a load factor of at least 6.0. Most modern aircraft are designed so that if all of the passenger seats are filled, the fuel tanks are filled to capacity, and the baggage compartments are loaded to their maximum authorized weight, the aircraft will exceed its maximum authorized weight. This allows some operational flexibility. Longer flights requiring more fuel can be made with fewer passengers and less baggage. Shorter flights requiring less fuel can be made with more passengers and more baggage. As aircraft age, their weight usually increase. Repairs and alterations are usually the major source for this increase. Aviation maintenance technicians conducting annual and 100-hour inspections must ensure that the weight and balance records for the aircraft are current and accurate. Residual fuel is the fuel that remains in the aircraft when the fuel tanks have been drained. The weight of the residual fuel is part of the empty weight of the aircraft. The amount of residual fuel and its location relative to the datum are normally found in Note 1 of the Type Certificate data sheet. An aircraft's useful load is determined by subtracting the empty weight from the allowable maximum gross weight. An aircraft may have different useful loads depending upon whether it will be flown in the normal or utility category. The useful load usually consists of items such as the fuel, crew members, passengers, baggage, cargo, removable ballast, potable water, and sometimes engine oil. The empty weight center of gravity of an aircraft is the center of gravity of an aircraft when it contains only those items specified in the aircraft empty weight. The empty weight center of gravity range is an allowable variation of travel within the CG limits. When the empty weight center of gravity falls within this range, it is impossible to exceed the empty weight center of gravity limits using standard specification loading arrangements. The zero fuel weight is the maximum allowable weight of a loaded aircraft without fuel. The tare weight is the weight of all extra items such as chocks, jacks, or blocks on the weighing scale. The tare weight must be deducted from the scale reading. The jack point are approved locations for jacking or raising an aircraft, and they can be found in the appropriate service manual. The center of gravity of an aircraft can be found by use of the following formulas. First, find the individual moments at each weighing point by multiplying its distance from the datum by its scale reading. Secondly, total all of the moments and total all of the weights. Divide the total moment by the total weight, and this will give you the center of gravity in inches from the datum. Be sure to pay special attention to the positive and negative signage of each arm, weight, and moment. Now let us do a weight and balance calculation for a typical light airplane. In this particular airplane, the datum is located at the forward tip of the spinner. The nose gear is located 32.7 inches aft of the datum. The main gear are each located 86.3 inches aft of the datum. The nose gear weighs 173.6 pounds. The right main gear weighs 642.9 pounds, and the left main gear weighs 644.2 pounds. For the first step in this process, we'll create a 4-column chart, an item weight arm moment chart as depicted here. In the third step of this process, we will list the 3 items for which we have weights. In this example, the nose gear, the right main gear, and the left main gear. In the next step, we will input the weight and arm for each item in the chart. In this step, we will calculate an individual moment for each item by multiplying its weight by its arm. For the nose gear, we multiply 173.6 pounds by 32.7 inches to get us a total moment for the nose gear of 5,676.72 inch-pounds. Likewise, we calculate a moment for the right main and for the left main. Once we have calculated moments for each individual item, we sum those moments to come up with one total moment. We sum the weights of each item to come up with a total weight. Once we have a total moment and a total weight, we divide our total moment by the total weight to get our center of gravity. In this example, we divide our total moment, 116,753.45 inch-pounds, by our total weight, 1,460.7 pounds, to give us 79.93 inches. The center of gravity of this aircraft would therefore be 79.93 inches aft of Datum. Now let us see how we solve a similar weighing problem, but one where one of the weighing points is forward of the Datum. In this example, the nose gear is 15.7 inches forward of the Datum. The main gear are 65.9 inches aft of the Datum. The nose gear weighs 201.3 pounds, the right main weighs 816.4 pounds, and the left main weighs 813.9 pounds. Again, we will create our item, weight, arm, and moment chart as in the previous example. Then we will add the three weighing points under the item column: our nose gear, right main gear, and left main gear. Then we will input the corresponding weight and arm for each item into the chart. Note that the arm of the nose gear is forward of the Datum, so therefore it is a negative value. We then calculate the moment of each item by multiplying its weight by its arm. Note again that because the arm of the nose gear is negative, the product of a negative arm and a positive weight results in a negative moment for the nose gear. Once each of the individual moments have been determined, we add them together to get a total moment for the aircraft. We then find the sum of the weight of each item to determine the total weight of the aircraft. And now, when we divide our total moment by our total weight, we get a center of gravity for this aircraft of 56.93 inches aft of the Datum. The total weight and empty weight center of gravity for a tailwheel aircraft are determined in the same manner as they are for a tricycle gear airplane. In this example, you will see that the Datum is located some distance forward of the aircraft. The main gear and tailwheel are all aft of the Datum. the weights and arms of each weighing point are given. Again, we will create our item, weight, arm, moment chart as in the previous examples. Then we will add the 3 weighing points under the item column. Next, we input the corresponding weights and arms for each item to the chart. We then calculate the moment of each item by multiplying its weight by its arm. Once each of the individual moments have been determined, we add them together to get a total moment for the aircraft. We then find the sum of the weight of each item to determine the total weight of the aircraft. And now we divide our total moment by our total weight to get a center of gravity for this aircraft of 77.37 inches aft of the datum. In some instances, the location of one weighing point may be given in reference to another weighing point and not directly to the datum. When this occurs, we must find the location of that weighing point in reference to the datum. In the previous example, the tail wheel could have been listed as being 108.9 inches aft of the main gear. To find its distance from the datum, simply add the distance the main gear lies from the datum to the distance between the main gear and the tail wheel. In this example, we would add 72.3 inches to 108.9 inches to get 181.2 inches as the distance from the datum to the tail wheel. How would this work if the datum lay between the 2 weighing points? In this example, we have the nose gear 15 inches forward of the datum, and the main gear lies 59 inches aft of the nose gear. Remember that since the nose gear is forward of the datum, its value is negative. Add the distance from the datum to the nose gear to the distance from the main gear to the nose gear. A negative 15 inches plus 59 inches equals 44 inches, which is where the main gear lies in reference to the datum.